PS2 due today or tomorrow if you take a late day. Are there any questions or problems related to PS2 or anything else? Yes?
When you're using a delegate to get the variable values, where are these values?
Well, okay, so he asks when you're using a delegate to get a variable's values, where are the values coming from? Well, someone called the evaluate method and passed in that delegate. So they created the delegate, so just the code for the method that got passed in. So think about where we're headed. What's the relationship between a formula and a spreadsheet? Can you imagine? Yeah?
Some cells use formulas.
All right, cells contain formulas. Can contain formulas. So every cell that contains a formula, there's a formula object. Okay? So it's good if formula objects are as small as you can get them, which is one reason you don't put stacks as instance variables, because suddenly all your formulas are bigger than they used to be. Now, when would you evaluate a formula that's stored in a spreadsheet? How would a spreadsheet use the evaluate method? Yes?
Say when there's a change or when it's valid.
Okay, so when something changes in the spreadsheet, some cells have to be reevaluated because changes propagate. And that means formulas have to be reevaluated. So every time there's a change, some number of formulas will be reevaluated by calling the evaluate method. What parameter will the spreadsheet pass to the evaluate method when it needs to have the method evaluated? Or let me ask you another question. What are the variables in a formula when the formula is in a spreadsheet? What will the variables be? Cell names. So you pass in that delegate to the evaluate method to have a formula evaluated. What will that delegate do? How will it find values of cells? It'll look up the value in the spreadsheet, right? So the delegate is what ties the formula back to the spreadsheet. When the formula is being evaluated, it's going to have to decide, okay, what's the value of A3? So you ask the delegate, what's the value of A3? And the code that's actually run is going to be looking up the value back in some data structure inside the spreadsheet. So that's how it all ties together. Someone else had a question about PS2 before I got sidetracked on that. Yeah?
How are we supposed to deal with the negative numbers again?
Well, he asked, how are you supposed to deal with negative numbers? You cannot have a formula with a negative number in it. Okay? So you can't have a formula like -5. You can have 0 minus 5 if you wish, but you can't have -5. That doesn't mean you can't have formulas whose values are negative numbers. That's something completely different. So certainly the value of a formula can be negative, and there's no problem there. Now, why don't I let you have negative numbers? Why not let you put things like -5 or -x? Yes?
Does it start to screw with the minus sign?
He says it starts to screw with the minus sign. That's not how I would put it, but the bottom line is, the algorithm I gave you is complicated enough dealing with precedence rules. The more operators we add, like unary minus, the more, the rules get more and more complicated, and the algorithm gets more complicated. So this is just a trade-off, just to try to keep things simple. Any other questions? Yeah?
The variables allowed to be negative, though?
Sure, the values of variables can be negative. Yeah. Any other questions? Okay, and remember, in the end, you need to commit the solution you want to grade on your PS2 branch, and then take the hash code for it, or the prefix of the hash code, and submit it. If you're using a PS2 work branch, that means that you need to check out PS2. Double click on it if you're using Visual Studio. Anyway, make PS2 your current branch by checking it out, and then merge into it. Merge from PS2 branch into PS2. And don't forget to commit to GitHub, because that's where we're pulling your commit from your grade. Okay, now, PS3 will come out soon, as will your grades for PS1. And anyway, next week you'll be busy working on this. Now, I just know from experience that I'll have questions about this, so I'm heading them off and teaching you something about specifications in the process. Okay, make sure I have the right level. Okay, so you'll be reading lots of specifications in this class. Next week you'll be creating a class called Dependency Graph. It's also a key component of the spreadsheet because in a spreadsheet, cells depend on each other in different ways. And the dependency graph is designed to capture the way that cells depend on each other. And when you read a specification for a new type of data, such as a dependency graph, you've got to understand, first and foremost, what is the abstraction? You have to explain how people that use this class are supposed to think about it. So if I create a class that represents rational numbers, provides ways to construct rational numbers, and provides ways to add, subtract, multiply, divide, and so forth, rational numbers, then really all I have to say in the comment is, this class provides rational numbers. Because we can assume people know what rational numbers are, which is fractions. So that's the abstraction. When people use these objects, they're supposed to be thinking in their head of rational numbers. They should be visualizing rational numbers. But when I assign you a dependency graph, I can't just say, this class provides dependency graphs. I need to tell you how to think about dependency graphs. So this would be a comment, a part of the comment that would appear explaining what type of object, what kinds of new objects dependency graphs provide. What are dependency graphs? And this says, a dependency graph can be modeled as a set of ordered pairs of strings. And then I even say what an ordered pair is. Two ordered pairs are equal if and only if the first equals the first and the second equals the second. S1 equals S2, T1 equals T2. So I've given you some terms and some notation to use. So a dependency graph is a set of ordered pairs of strings. And then it says, a couple more definitions. Given a dependency graph, DG, it says if S is a string, the set of all strings such that the ordered pair ST is in DG is called dependence of S. Okay? And if T is a string, the set of all strings S such that ST is in the graph are called the dependees of T. So that's defining dependence and dependees. Just some more terms that are needed to understand dependency graphs. So at a high level, you should now have a pretty good picture of what a dependency graph is. Okay? And if you don't, now's a good time to ask. And if you won't ask, I will. So, right, let me just give you an example here. Is this a dependency graph? Under my definition. Okay, why not? What is a dependency graph? It's a set of ordered pairs of strings, right? Is that a set of ordered pairs of strings? Sure it is. It's the empty set of ordered pairs of strings. So that's a dependency graph that contains no dependencies. Okay, what about this? Is that a dependency graph?
Yes.
Sure. It's a set of ordered pairs of strings. It's a set that contains one ordered pair. Okay, what about this? Is that a dependency graph?
Yes.
Sure, it's a set of ordered pairs of strings. A depends on B, B depends on A. Way to think about it. Okay, what are the dependents of A for that dependency graph up there? Okay, no one's very confident yet. Is it B? No, not B. Yeah? No. Well, let's go back and look. Let's look at the definition of dependence. That will certainly help. If S is a string, the set of all strings T such that the pair ST is in the graph is called the dependence of S. Okay? So, let's see. Where'd it go? I have to go back here. So, what do I write for the dependence of A? Yeah? The set containing B, right. Now you may think, I'm just being a jerk saying B is wrong. But it's the wrong type of thing. It has to be a set of strings. That's the dependence is a set. A unary set is different from the item in the set. Okay? What are the dependees of B? Right, it's the set containing A. Because here's a B, and everything that appears in that position when there's a B in the second position is in that set. Okay? So, I could add more things to this. So suppose I added A, C. A, D. Now, what are the dependents of A?
You have an extra bracket in there.
I do. Okay. Yeah, it's the set containing B, C, and D. Okay? Yeah?
Why is it not three separate sets?
Because the dependence of a string is a set of strings.
Okay.
It's a set of all strings that appear in the second position of ordered pairs where the A appears as in the first position. Yeah?
Does the order matter?
It's a set. So does the order matter? No. Okay. So these are just definitions at this point. You may think, so what use are the definitions? Why would I give these definitions? And they'll appear right at the top in my description, my class comment for a dependency graph. I spell all this stuff out. I'm trying to explain what a dependency graph is, and I'm defining these two terms. Why do I do that? Why define these things? Yeah?
To make it easier to implement.
He says to make it easier to implement, and that's getting at it. Yes?
To make sure we implement it correctly.
Well, I'm trying to write a precise specification, and this helps write the correct specification. So yeah, that's good as well. Yeah?
Is it for people who are going to be using it but they don't quite know what it is?
Well, my audience is both the people who are going to be implementing the class and the people who are going to be using the class. And they need to agree on what a dependency graph is. Yeah?
It would be the same reason why we use method contracts. It explains exactly what it does.
Okay. Make an analogy with method contracts. Bottom line is, I'm defining these terms because I'm going to use them later. Right? That's why you define things. You don't define them just to define them. You define them so you can use those definitions later. So let me show you what I mean by that. So I will have specified what a dependency graph is. Wrong slide, right here. And then, you'll find that. I think that's that's a method in the dependency graph class. And it says enumerates dependees of S. But what does it do? That's all I need to say. And you should be able to figure out how to implement from that. Now, people will tell me that's an incredibly vague specification. And I will say, no, that is completely precise. I precisely defined what dependees is. So what should it do? Yeah.
It should create a I-numerable string array of T from dependencies S.
Okay, so yeah, dependencies, at any given time, your dependency graph is going to have some ordered pairs in it. And so whatever string S is passed in to get dependencies here, you calculate the dependencies of S. That's a set, and you return it. You turn it to an I-enumerable and return it. Okay. Now, how do you go about calculating what are the dependencies of S? What's that?
Is it the X?
All right. You said, is it we started talking about ordered pairs there in front here. It depends on how you represent dependency graphs, how you go about figuring out the dependencies. I will tell you this. If you represent your dependency graph as a set of ordered pairs, you will not be happy. It will be far too slow. So, why am I telling you to think of a dependency graph as a set of ordered pairs, and then telling you had better not implement it as a set of ordered pairs?
Pairs are easier to understand.
Right. In the specification, I'm using words that are easy to understand, so I can explain precisely what I have in mind. But like in many classes, Jay, that you implement, the most straightforward possible implementation may not be efficient enough. You've got to work a little harder to get something. I want it to be fast, not just work. So, if you were representing your set as a set of, your dependency graph as a set of ordered pairs, then you had to calculate the dependencies. You'd sort of sift through the dependencies, and pull out the right values, and return them. But if you're using a different representation, it's up to you. That's an implementation detail. I'm interested in the abstraction. So I'm just saying, whatever you return and however you calculate it, it had better be the dependencies of S. Now, what does it mean to return an I-enumerable? Is that something strange or esoteric, or is it? Okay, what would be one possibility? Yeah.
It means we can iterate through it.
It means you're returning something that can be iterated through, such as what? What?
String.
Well, it has to be an I-enumerable of string, so a string would not be you couldn't return a string. Yeah?
An array.
Okay, an array. What else could you be returning? A binary search tree, right? You could be returning a tree set, a hash set, an array list, a linked list. Or you could be conjuring up the I-enumerable with an iterator like I showed you. All those will work. There are lots of things that are I-enumerables. That's an interface. Plenty of things are I-enumerables. So why am I not tying your hand? Why don't I say you must return hash set of string? Yes?
Is this implementation allow you to use yield as well?
Sure. Right. That's what I was saying. You could use an iterator with yield return to produce the result for you. Right? So what was the question I just asked? Because I just forgot it.
Wow, specify it more.
Right. Why don't I just say hash set of string and be specific? Why am I saying I-enumerable? Yeah.
You don't need it.
You say I don't need to?
Well, you don't need a hash set. If you
Right.
just want to go
I don't specifically need a hash set. The only thing I care about is I can iterate through the strings I get back. So I no need to tie your hand. You can decide what to give me back. Anything's okay as long as it's enumerable. So that gives you freedom, and I'm just telling you what I care about. Okay. So what I'm trying to head off is anyone telling me next week that this isn't entirely precise. I've told you what a dependency graph is. I've told you what the set dependencies of S is. So your method produces that. Okay, here's another one. I need to show you the whole thing. So it says removes all existing dependencies of the form RT. Then for each S in new dependencies, as the dependency ST. All right, so what's that going to do? How will that affect the set of ordered pairs with which we're modeling a dependency graph? Yeah.
If we're thinking in terms of A, B, C, and D like we were before, it would switch A to something like X.
Not,
X, B,
yeah, that's, I see where you're headed. That's probably not the best way to put it, though. I mean, the best way to put it is the way I put it here. It removes all existing dependencies of some form. So any dependency for which T is the second element, they get taken out. And then what gets put in? Well, what gets put in are a bunch of new dependencies that have T as the second part. Where do the first parts come from? From this parameter. This parameter is a collection of strings. So you add, for every string, if this contains the string, A, B, C, then you're adding AT, BT, CT back into the dependency graph. So when he says switch, that's, it's sort of changing that first part of the ordered pair and stuff. So this explains the method in terms of its operation on the way that we're modeling dependency graphs. Now, the challenge in implementing a dependency graph is you're using some other data structure. And you've got to be able to look at your data structure and understand, okay, what are the dependencies that are represented by this data structure? What do I have to do to this data structure to calculate the dependees or the dependents? What do I have to do to this data structure to do this manipulation? You have to understand your data structure in ways that I don't in order to use your class. Yeah?
As far as vagueness goes, this explanation doesn't necessarily explain, like, say, there's like 5 dependees, right, that comes up with it there, a form T, and then the string new dependencies have, like, say, 3, like in A, B, and C.
Yeah.
How does that get handled? That doesn't just silly.
Sure. You take out all the 5 that you said there's 5. You're saying there's 5 pairs of the form RT.
Yeah.
So you take them all out.
Okay. And if there's only 3.
And you put 3 back. That's what it says to do. It doesn't say it'll be the same size. I mean, maybe this doesn't change the dependency graph at all. It takes some out, puts some in. And, there may be different numbers being taken out and put in. Why have such a screwy, that seems like a strange operation. Where did it come from? How did I dream of how did I imagine that up in order to put it in my class and ask you to implement it? Am I just providing you busy work? Yeah?
If you change one thing that's on the front of a lot of lists, that program could easily fix all of it.
Okay, so he's imagining a program where this would be useful. What program was I imagining when I did this? Spreadsheets. I implemented the spreadsheet and I said, this would be a useful operation to have. So I put it in. So it's there because I know when you implement the spreadsheet it will be useful. Yeah?
So wouldn't cells be represented as like a set of ordered pairs in your spreadsheet?
No.
If you want to like zero out an entire like row or column.
No, cells aren't representing the dependencies. It's when you have 2 cells that depend on each other. I mean, suppose you got cell A1, and then A2 contains a formula like A1 times A1. Right? Now cell A2 depends on A1. A2 is a dependent of A1, and A2 is a dependent, A1 is a dependent of A, well, it goes one way or the other. But that's the kind of dependencies I'm talking about. Where you actually use this is when you replace the formula in a cell. Suddenly, if you replace the formula, things that you used to depend on, you never depend on, and suddenly you depend on a whole different set of things. So that's what that would be for. All right, so you'll be digging into this next week. I usually wait until Tuesday of next week, the typical semester, to show this set of slides, but I thought maybe I would get ahead of the game here. So. Any last questions about it? Yeah?
Is it just these 2 methods that we're
Oh, no, there are more methods. These are the only ones I wanted to talk about. Oh, there's another. Okay, this is just saying what I told you before. Don't take this to mean that you should actually represent your dependency graph as a set of ordered pairs. I guarantee you there'll be a grading test that will fail if you do that. So first thing is to understand what you're doing. The second thing is figure out a good data structure for it. But that's why I took 2420. So you know some good data structures. Okay, trying to decide what order to do things in. I think I'm going to do it. I just changed my mind about things. So I'm going to show you a new, something in C# that's different from, say, Java. And I'm going to make this bigger before I do that. All right, I want you to first look at what's up here, which is a class. So I've created a simple class. It has two public properties. They have both getters and setters, name and age. And then the constructor initializes name and age. Okay, so that's easy enough to understand. Incidentally, why does it keep telling me I wrote this? Don't I know I wrote this? Why does it have to say it? Written by Joseph Zachary 2 days ago. What the heck? Yeah?
You've got multiple people working on the same project. It's nice to know who's working on what.
Right. It's useless if they're only working on the project. Maybe the 2 days ago is interesting. But when you're working with other people, it's really valuable. Well, I just stopped working. Oh, Joseph Zachary edited it last. You know who it is. All right, so that's what's called a class. You know that. Now we're going to look at person 2. And what I want you to notice is it is character for character identical to person 1 other than the 2's, except for that right there. So this thing is defined as a struct. So it's a struct, not a class. Okay. So what we've got to figure out is, what's the difference between a struct and a class? Now, if you programmed in C or C++, you may think you know the answer. The struct keyword is in C and C++, but it means something different there. So it's the same word, but different meaning. Yeah?
Is it anything like an interface?
Nope, it's nothing like an interface. It's very similar to a class. Yeah.
Is that a value type?
Well, that's what it says up there. It defines a value type. So here's the deal. In Java, when I teach Java, I think there are 7 or 8 primitive types. Ints, booleans, doubles, and so on. And you learn they're different. They behave differently from objects. Okay? And in particular, when objects are stored indirectly, right? Objects out on the heap, and a variable that contains an object actually has a reference to the object. It's stored indirectly, so 2 variables can have a reference to the same object. Primitive types, when they're used, when they're passed as parameters stored in variables, they're just copied around. So a struct, the idea behind a struct is to allow you, the programmer, to define what you might think as new kinds of primitive types. But rather than call them primitive types, because they're not primitive anymore, they're user-defined, they're called value types. So what you create with classes are reference types. What you create with structs are value types. And there's a difference how value types and reference types are treated. So the things you think of as primitive in C#, ints, doubles, and so on, those are also value types. So Java doesn't let you create new value types. C# does. We've got to see what that means. So let's go see them used in action. So first of all, you see there I create P1, which is, I create a new person. So P1 is a variable that, what does P1 contain after I do that? Think of P1 as being a location on the runtime stack. What is stored on the runtime stack in P1's place? A reference, an address in memory of the object is actually sitting out on the heap. Now I do person P2 equals new person 2 Jack 21. What will be stored on the stack where P2's place is? The actual, what we think of as the object, the actual struct. It won't be a reference to something out on the heap. It'll just be there in the stack. So Jack and 21 are both stored there. well, Jack is a string, so there'll be a reference to the string. But anyway, there'll be two spots that we think of as P2. So it'll be physically stored there. It's not stored indirectly. Yeah?
So does that mean we can compare them like using double equals since we're not comparing references?
Well, yeah, we'll talk about double equals and such later on. So let's just get the basics down right now. So now I have this method called older1, okay? And older2. Let's look at them briefly, then we'll come back. Older1, it takes in a person. It increments that person's age. So we're adding 1 to the age and returns. Older2 does the same thing. It takes in a person 2 and increments its age. All right, so what happens when we pass P1 as a parameter to older1? Reference is passed. So whatever is sitting there, the reference that's sitting in P1 is copied up to older1. This object on the heap is incremented, and then the method returns. And so what will happen then if we looked at P1? Yeah, the age has gone up. Okay? Because we have this reference pointing to it out here. We pass it up here, pointing to the same thing. This object changes. After we return, we're still referring to the same object, so it's changed. Now, what happens when we pass P2? The object is copied. The struct is copied. So the whole P2 is right here on the stack. All those bytes are copied up above. Then what changes when we increment the age? This thing up here is modified. And then when the method returns, the original is not modified at all. We modified a copy, not the original. Okay? So that's an important thing to realize. Typically, you don't create mutable structs. Not such a good idea. Because if it's a mutable struct, that means you got to be careful when you pass as a parameter, because if something changes it, it won't change the original version. Now what if we insisted, I want to be able to increment the age of one of these person2 objects, or person2 structs. What would I have to do? What's that?
Return the whole object.
Well, that would work. I could modify it and then return it and assign it back on top of the old one. That would work. What if I wanted to keep the method void, though? Yeah?
Pass by reference.
Exactly. Pass it by reference. So then you're passing, you're not copying the object up, you're passing a reference to the place that it's stored. And then the original object would be modified. So I'm going to leave you with that thought. We're going to take a short break, and then we're going to look at some slides that animate what's going on. All right, let's get started again. So I wanted to say a word about Piazza. One feature of Piazza is it shows the average amount of time it takes to get I think it has to be a public question answered. And right now we're at 8 minutes. In the other class I'm teaching, 4150, we're at 11 minutes. So I think there should be a contest between two classes. What will help is if you guys answer questions, right? Then there are more eyes answering. So let's win the contest with 4150 by having students that know the answers, putting the answers up.
What do we get?
What's the prize? No.
You could just put a fake answer out there and get
Don't
score down to
we
one.
want good answers. Yes.
So in Java, you're able to use primitives for generic. What about with value types that we make in C#? Do we have to make an object for them?
No, you can use, I mean, in C# you can use ints, primitive value types, as generics. And the reason is because it was designed in the language from the start instead of being cobbled on in the middle. Yeah?
So I had a question about construction with the struct. We called the new operator, but it's putting it on the stack. And I always thought new allocated space on the heap.
Well, that's new does allocate space on the heap when you're creating an object of a class. But when you're creating a struct,
And you always have to call new with the struct.
yeah, you have to call new. So yeah, you have to know what you're creating when you say new. And it's technically wrong to say that structs are always stored on the stack. The right thing is structs are stored in place. So for example, look right here at this array. This is an array of ints. And that's a reference type. Why are the 7, the 3, the 9, and the 1 stored in the array instead of being stored indirectly with references to them? What is it about ints that tells us they're stored in the array instead of we store references to them in the array? They're value types. So if we had an array of person2 objects, what would it look like?
An array of references.
It would not be an array of references.
Oh, it'd be an array of
Person2 is a struct.
Oh, okay.
And so if this were an array of this is a, what did I call it here? V. This is a V object right here that's stored on the stack. If we had an array of these things, there'd be one of these in the first array location, another one of these in the second array location. So they're stored, value types are stored in place. Objects, the reference values, are stored at a level of indirection. Yeah?
Why would you want to use this functionality over using a typical object?
Okay, he's asking why. Why do we have them? Okay? I'll just briefly say that I'll look at it a little bit more later. But if you're creating lots of things with a small memory footprint, you can use space more efficiently if there's structs. Because an object carries with it not just what I'm showing you here. There's an additional reference, additional pointer stored in every object that points back to the class. And you don't need that for a struct for various reasons. So structs are usually used for immutable things with small memory footprints. Like suppose you want to create a rational number class. It would make sense for that to be a struct. Let's just see, though, how this interacts with our stack model. So what I've got here is, this is a stack frame for the method f. And you notice over here, f has a variable a, which is an array, n, which is an int, v, which is a struct, and r, which is an object. So there's that struct right there and the object up there. They have the same properties, but one's a class, one's a struct. So this is what the stack frame looks like. A is a reference type, so it refers to the array on the heap. N is a value type, so it's stored in place. V is a value type, so it's stored physically on the stack. This is stored as an object of a class, so it's stored indirectly. And you can see already, I've just sort of used 3 chunks of memory for this. And I'm already using these 3 out here, plus this. Plus, there's actually another pointer I have to store here I'm not showing that I mentioned that points off to the class. So that has a bigger memory footprint. Furthermore, if I want to operate or get the value of this thing, I just go to the stack and pull it out. If it is stored on the heap, I got to go here, follow a reference, and pull it out. So it's also slightly more efficient that way. It's just, it's there so that people that are really trying to engineer that last bit of speed into a program has a chance to do it. Okay, so what we're going to see now is what happens when we call, let's see what I'm calling. I'm calling some method G. All right, now I'll show you G. Okay, so I'm calling G and I'm passing it in as a parameter. So what's the stack frame going to look like for G to make this method call? It'll get pushed onto the stack. What will be in the stack frame? What's that? Remember, stack frame contains parameters and local variables, so what will the stack frame for G contain? Yeah? Well, not initially. What variables will be stored in the stack frame? Not N. M. M is the parameter. So what happens is, this red is just to separate the stack frames visually for us. We create a stack frame for M, and whatever is stored in N is copied up because we're passing the value of N as a parameter. And then what happens when we change N to 20? It changes, but then when we return, it's like it didn't happen. You're familiar with that. All right, let's look at a new G. Now let's pass N by reference. So what's it going to look like? Right, we pass a reference to where N is stored on the stack. So now what happens when I say M gets 20? It just comes down here and changes that to a 20. So that's just called by reference like we saw before. I'm trying to make an analogy to how we treat primitive types to how we treat value types in general. Okay, what happens if we pass element 1 of the array A by reference? What reference will be stored up here in G stack frame? What do you think? We'll start here. Where will it go? Right, it'll go there. You're passing a reference to where the parameter is actually stored. So what happens when I say M gets 20? Change the array. Okay? Now let's see what's in store. What if we pass R, which is an actual object of a class? What if we pass that to G up there? Okay? We just copy up that reference, so that's stored there. And now when we modify, we say s.name gets John. That changes. What happens when we say s gets we create a new object and store it in s? How's the picture change? Right, we'll create a new object. Why does it do that when I walk by?
Bump it. It came back here.
You're back there, but I don't see it here.
There we go.
Oh. No, what's happening is I'm bumping that cable.
Right. I told you I hate it being that plug there.
You're right as usual. Okay. I'll be careful. So what we're doing, we're passing that. Oh, we're about to create a new object up here, and this thing will point to it, right? And then when we return, so that affected what's stored here. It didn't affect what's stored there. It's two different storage locations. We return, and the object's been changed, and we see that, but we don't see the new object that was created. What do we have to do in order to see the new object, to have that new object be referred to by here? Yeah?
You'd have to return it so there's something referencing it, otherwise it just gets cleaned up, right?
Well, we don't have, returning it would work, but we can do it without returning it. Yeah?
Pass that by reference.
Pass it by reference. Did you say that before?
Yeah.
Yes. See, it's an all-purpose answer. So, what we're now going to do is pass, I guess I'm going to come back to that later. But I'm sure I'm going to have a question coming up that I'm going to call you to answer. We're going to pass V now. What's going to happen when we pass V? What will appear in the stack frame for G? What will W be? All this stuff copied up. So just keep that in mind. When you pass a struct, it's copied. When you return a struct, it's copied down. When you store it in a variable, it's copied into the variable, the whole thing, not just a reference to it, the whole thing. So this gets copied up, and let's see what we do to it. We change its name to John. So now we're operating on this. So we don't have any of it. We're not doing anything to this. What's going to happen when we say W equals new V? Where's it going to go? Yeah.
It'll override over.
Yeah. It'll just write on top of it. Same thing as this is an integer and you're storing a new integer to it. So it just goes in the old space. And when we return, it's like it didn't happen. What if we wanted to have these changes reflected down here? What should we do? Passive error? That's right. I told you. All right, so let's try passing the object by reference now. So we're back to R. We're passing it by reference. What's going to happen?
Point to the object.
So rather than, if we're passing it not by reference, it would contain a red pointer over to here. Instead, it's going to have a green pointer down to here. Okay? Now what happens when we say s.name gets John? It's going to come down here and then follow this and change that to John. And then we say, we create a new one and store it in S. So again, to store in S, it's going to come down here and store it there instead. So you get that picture. So when you return, you now have a reference to the old one. So that's called by reference using reference types. So it's sort of a double reference going on here. One reference is to elsewhere, then the actual reference to the object. Finally, we're going to pass this guy by reference. So our method has changed to pass a reference to a V object that we call W. So what's the picture going to look like?
It's pointing to this.
Sure. Yeah, it will be a green reference that sort of points down to this thing here. I have it pointing to this one because I had to point somewhere, but it's essentially referring to the whole thing. So when we say v.name is John, what changes? Jill gets changed to John. And what happens when we create a new one of those guys and just plop it in here? It just plops in there and we return. So that's called by reference. Yeah?
How do we actually get the reference of V since its store is in place? So how do we access these references?
Well, you
Repeat.
Okay, you're saying where did this green arrow come from, I think, right? So that arrow is stored on the stack. You as a programmer don't have access to it. Right? If this were C or C++, you could probably compute the location on the stack and actually print it out. This is done behind the scenes for you, but you can't find out the value of the green arrow. Right? Let's see. I think that's the end of that. Any other questions? We're going to go back now and talk a little more detail about the difference between classes and structs. So my advice was, the typical use case is structs should be small. Why should they be small? Because what? Well, if they're big, they'll take a lot of space on the stack, but they could also take space on the heap. Either way, they take space. Yeah?
They get copied every time.
Right. Copying is expensive if they're big. So since they're going to be copied everywhere, you want them to be small. So the idea behind a struct is you can use them to create small new types that don't have extra space overhead of a class. Okay, and then I said that structs are typically immutable, meaning there are no methods on them that modify, change its name or change its age. Why do we have them be immutable? Yeah?
Because if it changes in one part of the program, it might change for the entire program.
Well, it's actually the other way around.
Oh.
If they're mutable, if you pass one by value and it's copied and you change it, the change is not reflected back at the point of call, which maybe you're expecting because that's how objects work. So it can be confusing when they're mutable. Now, you may be stubborn and decide, dadgummit, I'm going to make large mutable structs. If you do that, what should you do to keep your program efficient? Okay, very good. Pass them by reference. so they won't be copied, and there's only one thing to be modified. All right, now I've got to go back to the beginning. And let's look at these, then we'll look at some code. So let's start here. Okay, so this is stuff we've already said. Classes define reference types. Structs define value types, which are analogous to primitive types in C#. And this is stuff we've just been illustrating. What happens when they're copied, when they're passed as parameters, returned as results, stored as variables. And, okay. All right, every object, we said that as well, every object has a space overhead of a reference to its class. So, like I said, this object also has to have a reference to its class to make casting work and to make primarily to make inheritance work. You don't have inheritance with structs. So that's stuff we've said as well. These are other differences. So as I just said, you cannot define structs with inheritance. That makes them more space efficient. When you declare a struct, we declare an object, it's just all that, essentially there's a spot on the stack where a reference could be stored. It's not initialized. Structs are always initialized. Structs have a default value. And the default value, ultimately a struct is made up of primitives at some level. So the default value of an int is 0. The default value of a Boolean is false. The default value of a double is 0. The default value of a reference is null. So basically what has happened is zeros are stored everywhere when it's initialized. So structs are initialized by default. Structs cannot have a zero argument constructor, which seems kind of weird, but the language is depending on the fact that structs are always zeroed out when they're declared. And that's done by a default zero argument constructor. If you were able to create your own zero argument constructors, the language would, maybe you'd forget to initialize something. So you can't write the zero argument constructor. The language does it for you. Okay, we had a question about equality earlier. The default is different. So what's the default definition for when two objects of the same type are equal to each other? If you don't implement any other thing, what's the default in the language?
The hashcodes match.
It's not defined directly in terms of the hash code. It turns out their hash codes will match, but yeah.
But they have the same reference.
Right, they're the same reference. So if you're trying to compare two objects for equality, you just compare their references. And if they're the same, then the object. So if two objects are physically the same, they're equal. Otherwise, they're not. Then you can go redefine equality, which people do. With structs, it doesn't have to do with where they're stored. It's just whether the corresponding pairs of instance variables are equal. So if you've got a struct that contains an int and a string, then by default, two structs are equal if their ints are equal and their strings are equal. So the default definition of equality is different. So if you use the keyword this in a method of an object, it refers to the object on which the method was invoked. It's just a reference that you can use. In a struct, this is sort of like a hidden parameter. It's a ref parameter to the struct on which the method was invoked. So it's just a sort of a backdoor reference to where the method was invoked. Okay. There's other fine print, but I've told you the important fine print. So let's actually look at some code here. Is this the one? Yes. Okay, so we started looking at this. This is where we first saw what happens when you don't pass them by reference. This was passing a person by reference here. So this shows a few more things. Structs don't have a double equals operator. So you don't compare structs with double equals, just with equals. This illustrates the default definition of equality, which you can look at if you're interested. There's a reference equals built-in thing in C# that tells you whether two objects have the same reference. It's sort of a way to get it. it implements the default notion of equality, even if you redefine equality. It always returns false for structs, because there aren't any references involved. That's more of the fine print. I'm going to look at something different. Okay, here is a class that implements rational numbers. And here's the class. Provides rational numbers that can be expressed as ratios of machine integers. Rats are immutable. So I've defined a class. I keep track of a numerator and a denominator inside every object, so that makes sense. I look at how I implement the, I've got three constructors. So let's look at this one first. This one takes in a numerator and denominator. If the denominator is 0, we throw an exception. Otherwise, we figure out the greatest common divisor of the numerator and denominator, and we normalize the numerator and denominator. So if I pass in 2 as a numerator and 4 as a denominator, what I actually store is 1 and 2. I want it in lowest terms. If I send in 2 as the numerator and -3 as a denominator, I turn it to -2 for the numerator and 3 for the denominator. I want the denominator to always be positive. Just makes things simpler. So the constructor takes care of all that for me. Now, what about right here? What's this method doing, this constructor method? It's taking in a single parameter. So it just gets the numerator, and the assumption is that the denominator is 1. So if you use this constructor and pass in 7, you've created the rational number 7. But how's it implemented? Yeah?
So when you call this function, this one refers to the other constructor?
Yeah, okay. So what you're saying is, before you run this code, call the 2-argument constructor and let it do its thing. So we're basically just using it, we're just calling 2-argument constructor, supplying the denominator of 1. Now, you don't see this in Java. What do you see? You see it called a super. So that's a slightly different syntax, but it's the same idea as in Java. It's like I called a super from a constructor. So what does now I have a 0-argument constructor that takes in no parameters, and if you call it, you get the rational number 0. So how do you suppose I implemented it? Yeah?
It says this 0, 1.
Yeah, well, I didn't do it quite that way, but yeah, I called the 1-argument constructor and pass it 0. Then it can call the 2-argument constructor. Or I could have, I could have done what you said. I just could have directly called the 2-argument constructor. I don't know. This appealed to me for some reason. Okay, so I can construct rational numbers. Let's see what else I can do with them. I can add them. Yeah?
So I just wanted to clarify, you said that this was equivalent to the super in Java?
In a constructor, yeah.
And then what would base be then in that context in C#?
I'm going to hold that to another time, because we'll talk about inheritance another time. All right. If you've been programming in Java, what's unusual about this method here? What things do you see that you don't understand? Checked. Okay, checked is pretty cool. So normally, if you multiply things, add things, integers, and they overflow, wrap around and become negative, it just happens and your answer is wacky. When you put checked around some math, it will throw an exception if there's an overflow. So it's less efficient because it has to keep checking about the overflows. But if it happens, you find out about it. So if you're worried about that happening, just wrap checked around it. And so if you try to add things that are going to be too big to represent as a rat, you'll find out. Okay, what else? Operator. Okay, this is called operator overloading. So notice how I'm defining it. I'm defining a static method called operator plus that takes 2 rats as parameters. Now they're only, so we're basically defining the meaning of what it means to add with the plus symbol 2 rational numbers. So elsewhere, I could write, if I had A and B are rational numbers, I could write A plus B. And I'm calling this method. Instead of having to do A dot add of B. Okay? So to do it, this has to be an operator that's overloadable. And I don't have the full list memorized, but certainly plus, minus, times, divides, mod are on the list. Operator keyword, the method has to be static. So I redefine what plus means for rat. Is this a big deal, or is it just, again, it's syntactic sugar, but is it important? Yeah?
I mean, it kind of helps make your code look cleaner. So instead of having to write, call a method every time you want to add two rational numbers, you can just do it on the fly.
Notation matters. Right? If you're a mathematician and someone shows you a program and it says A times B plus C, where plus and times have been redefined, I mean, that notation they're used to. They go, yeah, I understand what that is. But they say A dot add of B dot null C, they're going to go, huh? Well, I mean, so it is important. Notation's important. This is a very valuable addition to the language.
Does operator only exist in the context of a method header? Or?
Yeah, the keyword would just show up in the method header. If you try to just define plus directly, it's going to complain. It wants to see the operator before. So anyway, here's operator times. I've overloaded times there. And then I got tired and I didn't do the rest. Okay, here's a toString method. Nothing fancy there. If the denominator is 1, it just prints out the numerator, returns the numerator. Otherwise, it makes a fraction for me. Now, why don't I have to, I want the toString to produce a number in lowest terms. Why don't I have to work here and put it in lowest terms? The constructor did that for me. I'm guaranteed the numerator and denominator are in lowest terms because the constructor puts them in lowest terms. Okay, here's an equals test. So I got to decide whether this rat is equal to object O. So I cast cast O to be a rat. If that fails, this as operator will give me null. So either this cast will succeed or it will fail, and when it fails, it nulls out R. And so then I say, okay, is R null? Or is R not null, rather? And are the numerator and denominators the same? Now, I was looking at this today, and I saw that ... and I said, what's that? And it said, null check can be simplified. And I said, wow. It's always something new every time I teach this class. So this year, you can do this. If not, okay. So that's interesting. Okay, here I'm overloading the equals operator, the double equals operator. And I'm making sure that they're not both null. And if they're, then I just do the equality test. And it's suggesting I could do the same trick again here. Save typing. Here I'm overloading the not equals operator. And I'm just defining it to be not equals. And here I'm overriding Hashcode. And I'm overriding, well, let's take a time to look at what I'm doing here. Get Hashcode has a default definition in the base object class. I'm overriding it. When you override a method in C#, you have to say, I'm overriding it. And it has to be a method that's overridable. And this here, what would that method do for me? What am I defining there? What's a cast? So where you see cast is you'll see something like this. You'll have double D equals 3.5, and then you say int n equals int D. You're casting the double to be an int. Now, it can't be n, it has to be something else. So it converts. You're asking it to convert D to an int, and what it does is it truncates the fractional part. So now with this operator, I can say things like, I can say rat R equals rat of 7. I can now cast, I've defined a way to cast from ints to rats. The method gives a conversion from from ints to rats, and then I can use it like illustrated here. You wouldn't actually put this code in here. I just had to have a place to type it. So there are all kinds of things you can customize here that you couldn't do in Java. Okay. Yeah.
That's the implicit operator.
Oh yeah, implicit. So what that means is since it's implicit, I don't even have to put the cast. It's done for me automatically. Now if I say explicit, I think, or leave implicit out, I'm not sure which it is. Okay, I can say it's an explicit cast, and then you have to explicitly do the cast, or it won't let you, it won't allow it. But this is implicit, yeah. Thanks for pointing that out. Any other questions about that? Yeah?
So is that all those keywords that implicit and explicit used for is basically defining?
Far as I know.
Repeat the question.
You want to know do you see implicit, explicit anywhere else other than defining overloading casts? And I said, as far as I know, and the reason I say that is C#, unlike Java, Java libraries change a lot, but the Java language itself almost never changes. C# seems to change literally every year. It's always something new that I discover preparing to teach. Yeah?
This makes it so that you can cast an int into a array, right, and not the other way around.
Right. So if I wanted, I'd have to, I assume I could define one from rats back to ints, but I'm not 100% sure. Okay, now, I have another class called rat_struct. So it's just like what we just saw, except rather than representing the rat as using a class, creating a class called rat, I'm creating a struct called rat. And let's see what changes. So this is it. So you can see right here, I defined it as a struct. And it still has a numerator and denominator just before. And I have a 2-argument constructor that works just like before. And I have a 3-argument constructor that works just like before, and it puts things in lowest terms just like before. But what's missing? Let me ask a different question. How much space does it take to store, if you represent the rat as a class, how much space does it take to store a single rat? Just out on the heap. So there'll be 2 ints and a reference. So those are probably the same size. So each one is either 32 bits or 64 bits. Probably 64 bits these days. How about to store a rat if it's a struct? Just the 2 ints. So we're saving a third. We're saving a third of the memory footprint by using a rat. Okay? So there's a 2-argument constructor and there's a 1-argument constructor. What happened to the 0-argument constructor, the one that constructs 0? We're not allowed to define it because the default behavior is to 0 everything out. Which means what? What if we write our program and we create a rat and do it by calling the 0-argument constructor? We can call the 0-argument constructor. In fact, let me try something here. I'm pretty sure that if I just declare it like that, it's automatically initialized by the 0-argument constructor. So what would be stored in the numerator and the denominator if I use the default 0-argument constructor? They'd both be 0. Everything's zeroed out. So that bothers me now. Because how did I represent 0 before? When I stored both a numerator and the denominator. How was 0 represented in lowest terms? Numerator was 0, denominator was 1. Now it's numerator was 0, denominator is 0. So when I go to print out numbers, to convert to a string, I sure don't want to turn that print 0 as 0/0. That would be embarrassing. So what's this fact that I can't customize the 0-argument constructor? What does that imply about the rest of my implementation? What problems will that pose? That sometimes I'll have that 0 is going to be sometimes represented as 0 over 0. Yeah?
Could you just pass it by reference and modify the denominator so it comes back as 0?
Well, yeah, if I knew it was being constructed, I could change it, but I typically don't. I don't have a hook into the default constructor. Yeah.
Just validate and account for it.
Okay. So what he said, validate and account for it. What it means is that we've got to handle that as a special case. All our methods are going to have to be open to the possibility that there's going to be a numerator and a denominator that are both 0. So it's going to slightly complicate the rest of our code. Now this doesn't always happen with a struct. It just happens here because having a denominator of 0 is kind of awkward for me. So let's see what had to change about the code. Here's my add operator. So what's happening? I'm calling r1.normalize, r2.normalize, and what do you suppose they do? If the denominator is 0, it changes it to 1. Okay? So every time we go to work on something, we got to make sure we're not dealing with one of those weird zeros. And then it just works like before. So there's normalize. Well, it doesn't like the lowercase n. Here's toString. I normalize it first, and then I do that. Or I could have said, if denominator is 0, return the string 0. Else if it's 1, else. There's several ways I could do it. Here's the equals method. Let's see how that's different. I'm saying if O is a rat, then I do the cast, normalize R, and compare numerators and denominators. Now, otherwise I return false. This is giving me a fix. It says I can use if O is rat. I can do this. This is also new. So what that does is either, well, I don't know what it does. Let me go down and tell you what it does. I remember looking at this in my office and now I've already forgotten. So it's saying do pattern matching, rat R equals okay, yeah. What it's doing is if O is a rat, it does the cast and stores the casted thing into R. It just does what I was doing before, but in one step. So if the cast succeeds, it stores the cast in R, and then I can work on it. And here's my quality test. And staring at them, I'm wondering if they're really right, because I'm not normalizing these things. Doesn't it seem like before I check whether R1 equals R2, oh, in my equals method, I really think I should be normalizing. I better normalize both of them before I do anything. So there's a little bit of intellectual overhead to writing this because we've got to keep just dealing with that special case with zeros in the denominator. No big deal. So what we end up with, it works virtually the same. We don't have to worry about it passing it somewhere and having it modified because you can't modify. There's no method that changes a rat. You can't directly change the numerator and denominator once it's created. So it's immutable. It's small. So this is the ideal candidate for implementing a struct. Okay? Are there any last questions? Sort of got here at the end, went down the rat hole of details of C#. Yeah?
It seems really complicated that you can't set rat items when you initialize a struct.
Yeah.
Repeat the question.
He said it seems odd to him that you can have, essentially, you can't have default values that are used by the zero argument constructor.
Is that just kind of the way
Yeah, there's something about the semantics of the language depends on, I think for it to be efficient, when you allocate a struct, it just zeroes it out, right? And that's fast. It doesn't have to run any code. It just stores all 0 bits. And that only works if there is no default zero argument constructor. Okay? So you won't have to use structs this week, but you will eventually. So. All right, we'll stop there.